Good afternoon and welcome to the Purdue Security Seminar, live from Purdue University. Whether you are live in the audience or live virtual or not so live and viewing this as a recording later on. So I've had the great pleasure of knowing our speaker today for 8 years. Did you realize that? 8 years. Yeah. So our speaker today is Chris Jenkins. Dr. Jenkins is a principal member of the technical staff in the Systems Security Research Department at Sandia National Lab, a Department of Energy National Lab, in their Information Operations Center. Chris supports Sandia's mission in 3 key areas: cyber physical security research and high performance computing. Did I cut and paste something out that I missed?
2 key areas.
Okay, in these 2 key areas. Okay, you may want to go check that. But back in 2014, Chris did his very first trip to Purdue, and I had the great honor of being his host during that trip. We bonded well and have maintained contact and talked basketball, college basketball, whenever we have the opportunity. But Chris has been back to campus many times since then, as he is the principal investigator on a Sandia funded research project with several Purdue faculty members. Again, Chris, always great to have you back on campus, and thanks again for supporting our research mission as we support your research mission.
Thank you, Joe. Thank you for that introduction. Once again, my name is Chris Jenkins, and it feels good to be here back at Purdue University. As Joe mentioned, I think I gave my first presentation back in 2014, not realizing how many more times I would come back to Purdue to not only present here, but to do research collaboration with other faculty. So today we're going to speak about 2 different projects. This one called Moving Target Defense for Space Systems. It has completed, but it's some work that we did here at Purdue. We have 1 pending publication on this work, and then also we started a new research program here with Professor Bharat Bhargava at Purdue, and we're also going to speak to that a little bit as well. And also I have my esteemed colleague, Jason Hamlet, in the audience here as well. So for the first presentation, we're going to speak a little bit about why this work was done, give everyone in the audience some information about moving target defense and MIL Standard 1553. We're going to look at the MTD algorithm that we've come up with at Sandia, some of the features and attributes of that algorithm, look at the experimentation that we conducted to prove the algorithm works in real-time systems, and then also look at what the work we're doing with Purdue regarding the machine learning attacks, how they defeated our algorithm, and then by changing 1 line of code, making it much tougher to defeat. And then also we'll look at the second project that we're working on with Purdue right now that started this year called CRISP, and Purdue's impact for that project. So a little bit about the work before we get into it. So we were able to get a patent on the algorithm for this work and obtain copyright, which is just a fancy way to say that the United States government can use this software if they need to for governmental entities. The key results for this work is that we were able to reduce the adversarial knowledge by 97% during an exfiltration attack, and we'll get into that throughout the presentation. We're also able to quantify randomness, and also, based on the work that was done here at Purdue, improve the algorithm design to defeat some of the machine learning attacks. And you see a list of publications that have presented this work in, as well as a pending journal publication for some of the work done here at Purdue. So first, why is this work being done? What do we want to do? And so the first thing I mentioned is satellite systems, right? We want to look at ways to protect satellite systems. As some of you may have been aware, just like we had cyber attacks in terrestrial networks, space a lot of times is seen as the next frontier of where the cyber domain can go. And so a lot of our work, as Joel mentioned in my introduction, is looking at cyber physical systems. And in my particular case, some of those high consequence systems, to say if they are attacked, as most of these systems now are being connected to different networks in one way or another, we want to make sure that these systems stay protected. And so for this research, the hypothesis that we have is that the integration of MTD with real-time protocol can increase the cyber resilience. And so the 2 key research questions that we have: 1, can it be implemented? In our case, can MTD be implemented in a manner that maintains operational constraints, i.e. the protocol still works as it intends to? And 2, can we provide quantitative evidence that MTD does in fact improve cyber resilience. And we believe the uniqueness of this work is that we're focusing on real-time SWOT constrained systems. And while we can be a complement to anomaly detection is not required for our MTD system to work. So now we'll get into the background. I can actually teach a whole class just on MIL Standard 1553, but for the purposes of this work, this is a military protocol that's been around since the 1970s. Tried and true, a lot of military aircraft use it, satellite systems use it. The key concept that we need to take away for this particular presentation are what you see on the screen: the bus controller, the bus monitor, and the remote terminal. So typically a bus controller would be a mission computer or your aircraft. Your remote terminal would be something that may be a sensor, a camera, altimeter, or different sensors that you may have on your particular network. And then the last is the bus monitor, which serves as the same purpose as your flight recorder on your typical commercial airlines. And so here's just an example of a message that may go on the bus. And if you look at the actual, I guess, command in this case, it's called 3-R-1-32. And if you get into the protocol, you start to do what we call 1553 speak, but it means the bus controller sends a command to remote terminal 3. It's going to receive data at what's called subaddress 1. And in this case, 32 is going to send 32 16-bit words. So that's a little bit about the 1553 protocol. Looking at moving target defense is just a fancy way of saying it's a dynamic reconfiguration of your environment. So in terms of the graphic you see here on the screen, you have an attacker that's trying to attack a server. And the IP address is the moving target. And so by moving it around, it makes it harder for the attacker to actually attack and get access to your server. And so hence, in this case, the moving target is the IP address, and the defense is the fact that it hops around. So once again, our hypothesis is that MTD does in fact increase cyber resilience. So now we're going to dive into the design of our algorithm and also highlight some of the kind of raw features of the algorithm. So when we first came up with this idea, we did not want to come up with a MIL standard 1553, or in this case, 1554. We wanted to keep the underlying protocol, but still have a way to dynamically have nodes change their address. So just like in the previous example, you have IP addresses. In this case, you have 1553 addresses. We want to keep everything in sync. As you can imagine, if these networks on high consequence systems, a loss in synchronization could be catastrophic. And so but in addition to that, unlike IP addresses where you have 4 billion or maybe more, on these type of networks, you have 31 possible addresses. So we want to make sure that we still make it difficult for a potential attacker to guess the next address. And we also don't want to have any patterns in this, because one could argue that if after 1,000 variations, if I repeat that pattern could be predicted or known, effectively MTD doesn't exist for that system. And as always, if we put these messages on the network, we want to make sure that the node addresses only change when authentic commands are put on the bus. So these were the 6 constraints that we had when we first started this algorithm back in 2019. So without going into the detail of the algorithm at the very high level, we have a shared key and a nonce, and we push it into a randomness primitive, the output of that being a randomized array and another nonce that you could then, again, as we call it, pull the crank and keep generating randomized arrays in a new nonce. And so what you get is a 2D array, or as we call it, the state matrix. So how, having this state matrix, how would you use it? And so one of the ways that we use it is what's called the static addressing method. So if we have an index of 3 that comes out on the bus, and a node has a static address of 0, which is the same address as if MTD did not exist on the bus, it would pick value of 4 for this next address. And if we had a node that started with a static address of 4, and we saw an index of 3, it would have its next address as a value of 24. So the one thing that you maybe can pick out about this is that for a given index, you always get the same next address. And we'll see that in the future, because of that, the students here at Purdue University were able to defeat this algorithm. So as another way to look at the state matrix, instead of having static offset method or a static indexing method, we're able to have what we call a current indexing method. So using the same state matrix, in this case, an index value of 2 instead of 3, if we have a node on the address and it has a current address of 1, its next index is 3. And then if we have another index come out, in this case, for example, let's say it's still 2, that same node that now has a current index of 3, current address of 3, it's now going to have a new address of 13. And so one thing we learned for this particular way of addressing that it has a temporal locality as part of the addressing method. So whereas in a static case, the index of the next address is always the same, in this particular method, the actual next address depends on the current address. And we'll see why later on that was very important for some of the machine learning attacks. And so we have two other methods that we won't discuss in this particular presentation called linear static and linear current. But just note that these are the 4 that we're using, but we could come up with different methods. Most of the work that we've done here just use the static and the current method of indexing the state matrix. So now we're going to go through some of the attributes that we did when the algorithm was first created. So first of all, we wanted to know what is the size of the matrix. So assuming that every address takes up a byte, we can see here that as we go up to 65,000 arrays, we reach our peak max of around 2 megabytes. And so we believe, looking at some of the future slides that will show, that we could get away with about 128 or 256 arrays. And so we believe that a lot of this work could be done in smaller microprocessors and even in microcontrollers. So here, and this is on an Intel processor, in this particular case, it's a 6th generation processor, Core i7. We wanted to figure out how long does it take to generate a particular round of the algorithm. And looking at 65,000 rounds, which is more or less steady state, it takes somewhere shy of 300 microseconds. Now, this bus runs at 1 microsecond. And so if it takes you 300 microseconds to potentially generate an array, we would advise that do all of the state generation ahead of time and not try to do it on the fly, though you could if you had a fast enough processor. So now that we have the state matrix, we wanted to understand, does it provide enough entropy? Entropy being one of those metrics we wanted to look at for our algorithm design. And so what we see here is that we generated 65,000 indexes and then looked at the next address and then put that in a particular bucket here on the histogram, excuse me. And what we found out is that having a state matrix of 256 columns performed from an entropy standpoint very similar to having 65,000 columns. So our argument from looking at this data is that we could have smaller state matrix and still get good entropy performance. So we took that same data and looked at it a step further and looked at 3 different sets of data. State matrix of 512 columns, 8,000, and 65,000. And we wanted to see if we took every single possible node on that bus, so from node address of 0 to node address of 30, we wanted to see how long it would take for every single possible node to be assigned another address value at least once, or every other possible value at least once. And the key takeaway from this graph of this chart is that the static cell offset method has a much higher average, I should say has a higher average and a higher standard deviation compared to the other 3. And the key thing that we found interesting about that is that as we go through the rest of this presentation, we'll start to show you different windows to look at this data. And those windows will all kind of agree that the static method more or less should not be used, or we should say the static method performs worse than the other 3. So here we have another window we want to look at. I won't get into the details because I can spend probably 30 minutes on this slide alone, but we looked at 3 aspects of the state matrix in the algorithm: the offset method, the size of the state matrix, and how often we were to update the state matrix. And what we found out using these 9 unpredictability metrics is that the state size, the state matrix size, and how often you update the state metrics did not affect those metrics as much, the unpredictability metrics. But the actual offset method, the metrics did change a lot more, meaning that static had the worst performing. And as you went from left to right, moving over to linear current, we had a better performance in terms of the unpredictability metrics. And so even though we're looking at it from a different window, we can see that static performs worse than the other 3 types of indexing methods. So in summary, from this kind of looking at the raw data of the algorithm, we see that not all addresses are created equal. Some addresses are going to have more variation than others, but they are close, so not purely uniform distributed. But they actually have a very close distribution between something that is 256 versus 65,000. All addresses are going to be used. So there is no node on this bus that if it's node 5, let's say starts out at address 5, it will be assigned every other address at some point in time in the future, as opposed to certain nodes not getting assigned that address at all. You don't need a large matrix to have good entropy, but this is something that we were assuming that we want to have a large matrix, but we found out that we didn't have to. So that means that smaller processors and microcontrollers could use this algorithm if need be. And then also indexing to the state, we would suggest that you generate the state matrix and use it on the fly. Generate the state matrix beforehand and don't use it on the fly unless you have a fast enough processor. And there's different ways that you could try to minimize the state. And one of the ideas that we had is you store it every 8 rounds, and then anything in between there, you just generate on the fly. And so that could reduce the time, but we still would recommend doing everything ahead of time and then just indexing on the fly. So now we're going to move into experimentation. So we wanted to know that, hey, we have this algorithm. How do we know it actually works? And so we built a mill standard 1553 bus, and we wanted to do something very simple, just to test the algorithm. I believe this was done in the summer of 2019, 2 interns we had at Sandia. And so we wanted to try something that would be done really quickly and just really test the algorithm. And so we broke it up into 2 phases. 1, to calculate the 24th Fibonacci number, and 2, an exfiltration experiment. So in phase 1, we calculated the Fibonacci sequence, and we were sent what we call an MTD update command every X frames, and it's 2 messages per frame in our particular experimentation. Because it went very quick, we decided we're going to have something called generation, which is just calculating that 24th number over and over again to get the number of messages that we needed. And then in phase 2, we wanted to play the adversary, or the role of the adversary. And we wanted to say, if we know a particular node has the information that we want to pull out, everything going to and from that node, we're going to listen for. And we're going to look at that with MTD and without MTD. With the goal being that we want to quantify the reduction in adversarial knowledge, if any. So the way it starts off is that the bus controller, which could also be a mission computer, is going to send an MTD start message. The RT is going to take that nonce from the MTD start message, and it's going to create a hash and send it back to the bus controller. If the bus controller's internally generated hash matches, it knows that both the BC and the RT have the same state matrix without actually sending, or hopefully without leaking any information across the bus. Start the Fibonacci calculation. After so many frames, we send an MTD update, which just has a value between 0 and 127. The new addresses are used, and we continue calculating up until we get to the value of hexadecimal B520, which is the 24th Fibonacci number. And either we stop the experimentation, or if we need to generate more data, we'll keep doing what we call generations. And so just to visually kind of highlight that, in the MTD start, we have the 128-bit nonce. The MTD verify has the hash. MTD update has a single value. And of course, when we finish, we have the value B520. And it's a marker that we can always find using the bus monitor that we got the right value and everything is working as intended. So like I said before, we wanted to figure out what could an adversary pull out. And so on the left side of the graph, we have the percentage of messages that were exfiltrated. And then on the x-axis, we have going from left to right, we vary the frequency of how often we send out MTD update messages. And so what we found out is that the attacker would pick a random address and it would listen for that address. For a certain amount of time, what we found out is that we were able to reduce the information that that attacker gained with MTD on versus off by 97%. And so if you think of 1 divided by 31, it's around 3.2%. So experimental matched the theoretical estimate that we were intending to see. And so on the right side, same experiment, but the attacker knows the first address instead of guessing the first address. And so what we saw is that once we have a low frequency of updates, that because the attacker started on the known address, it was able to capture a lot more of the traffic. But we have a very small experiment, in this case, 50 generations. And we believe we went out to 5,000, 5 million. The graphic on the right will start to look like the one on the left, and you approach that theoretical estimate. So we wanted to crank it up a notch and get a really smart learning adversary. And so in this case, we assume, well, what if the adversary could learn the pattern, let's just assume, after so many frames? So for example, we had a period of 25. So after every 25 frames, we sent out an MTD update command. But the adversary could learn the pattern after 8 frames. Then they could exfil 70% of all the messages. If we took them 16 frames, they could exfil 40%. And of course, if they go above 25, they potentially exfil nothing, which means the adversary just has a better opportunity to just listen at one address and don't move. And so what it told us is that if you can model your adversary and have a system that can move faster than your adversary, it can make it very challenging for your adversary to ever figure out what is the next address. And so we want to look at machine learning. And this work, as I mentioned before, was done with Purdue. We're done here at Purdue University. And so before we go into the machine learning, we wanted to highlight a few aspects of what the students were looking at. So if you look at the screen, you have these circles. And like I said, this is 1553 speak, but the key importance of these circles are the first number. So if you look at the blue box, message 13 and 14, the first number is 1, which means it has a remote terminal address of 1. Message 15, this is what we call MTD Update Command, and it is a broadcast command, so every node hears it and has a value of hexadecimal 17. And from that, and we call that the index, but from that index, for message 16 and 17, the new address is 27. And so that's really the uniqueness of this work, is that by sending out that index, both the bus controller and the remote terminal can switch over to the correct address without hopefully leaking any additional information and maintaining the protocol, maintaining the same speed. And so just to go back to that real quick, what the students wanted to do is apply machine learning to see if I look at remote terminal address 1, I look at the hexadecimal value of 17, can I figure out that the next address is going to be 27? And so originally we had some other questions we wanted to ask, but as you all know, due to the pandemic, we were not able to answer all of those questions. Yes. Okay.
You got it. You go.
Oh, okay. I think you mentioned that based on the current address, it is determined what the next address will be. How do you determine from the current address what the next address will be?
So make sure I understand the question. So you're asking me, how do you determine the next address? So it depends on the indexing mode. So if you're in what's called the static indexing mode, given the index value of 17, I'll go back one, given the hexadecimal value of 17, so that's considered the index. And so in our particular algorithm, that index value of hexadecimal 17 corresponds to a column. And if in this case, the remote terminal address is 1. So in that column, you have the row of 1 per se. You have the column of 17 hex. Whatever that value is, that's your next address in static indexing.
And is that column known to like both the sender and the receiver?
Correct. So they both have identical state matrix. And the way they know they have identical is that a hash is sent between them before the process even starts. And so if they have the same hash, then they can guarantee they have the same data for the entire state matrix. So excellent question. And so what the Purdue students here were going to do is figure out from either looking at previous addresses, looking at the current index value, could they figure out that the value of 1, looking at the hexadecimal value of 17 for the index, is going to turn into 27. So as I was saying earlier, we had some other questions we wanted to ask and answer because of the pandemic. We had to really focus on different set of questions. And so we kind of down selected and said, well, what is the most important thing about this work? What would give the adversary a home run? And that's if they can predict the pattern of the next address. Because if they can do that, then effectively you have disabled and turned off MTD. And so in our particular case, the students decided to use, I believe it's called the long short term memory model. And I'm definitely not an SME expert, so the students definitely helped us out with this work. And we were able to vary the training size, but the test size always stayed at 20%. And so they had this metric called the F1 and the MCC number. And the key takeaway from that is the closer you are to 1, the better the machine learning model can predict the next address. So effectively, if you're above 0.9, 0.95, every single time you see an index, you know what the next address is going to be. You have defeated the algorithm. Home run, you win. Adversary wins the game. And so when we sent them this information, we use what's called the static indexing method or the static cell offset method. And going from left to right, on the left side, they're looking at 1 previous address. The next chart is looking at 2 previous addresses. And then the third chart follows on the right is looking at 3 previous addresses in addition to the index value. And as you can see here on the left side, once they got beyond 20,000 messages, they were hitting above 0.9, which means effectively they were guessing the next address every time. And so by changing 1 line of code, we were able to take that from around 0.95 down to less than 0.2, which effectively means it's the same as picking a random address. And so they were having a very difficult time at guessing the next address. So why do I feel like this is important? Is because when we looked at the unpredictability metrics, it showed that the way you index the state matrix mattered. Static performed the worst. When we looked at machine learning, static was predictable. When we looked at the previous chart, where I talked about the standard deviation and the average, static had the highest. So different windows were seeing the same exact conclusion. And then when we looked at current, it performed better in unpredictability metrics. In our particular case, the machine learning model could no longer predict the next address. Doesn't mean that no model can do it. It just means we were able to make the algorithm provide more entropy and remove some potential patterns that existed using the static method. So I mentioned before, we got a patent for this work, obtained some copyright for the government. We're also now working under NDA with the commercial companies, the startup company, on integrating some of this technology. And as we mentioned before, I think the key results from this work is that being able to reduce information to the adversary, being able to quantify the entropy and randomness in the algorithm. And towards the end of the work, we realized that while we focused on Mill standard 1553, the actual algorithm could be decomposed into 4 components. And if you were able to customize each of those 4 components, you had a generalized approach to actually designing an algorithm for IP addresses, CAN bus addresses, crypto keys, and maybe even some other attributes, depending on your system. So before I move on, are there any questions from that work?
We do have one. If an adversary is sniffing the bus and has access to all initial conditions, can they defeat the whole scheme, assuming that they know the MTD algorithm?
So what the adversary would have to have is that shared key. So the only thing the adversary sees on the bus, it sees the index going back and forth. It sees the hash. In our case, it's really a HMAC 256 or HMAC 512. And they see the nonce in the MTD start command. And without that shared key, we're going to make the argument that you cannot predict the pattern of next addresses. And to prove that argument, or at least to have more data and quantifiable argument, that's what the students here at Purdue did. They used machine learning. They did not have access to the shared key. With one method, they were able to predict it, and with a particular another method, they were not. And so I think given, just to address the question directly, given a sufficiently strong algorithm and given the information and attributes that an adversary could get on the bus, they should not be able to predict the next address unless they have the shared key. Hopefully that answered the question. Yes.
Is that hash that you're referring to, does that also serve to like seed the pseudo random number generator for the methods that were superior to static?
So the hash does not seed it, but the shared key does help with the seed. And the randomness primitive could use, in our case, I believe we used SHA hashing, but you could use symmetric cipher and either stream cipher mode, block cipher mode. You could use other primitives. It's just that once the work got going, the hashing worked for us, and we just kept going on, did experiments, did machine learning, other attributes of the research. But you could go back and try, AES 128, 256, SHA-3, and some other algorithms to see how they fare with unpredictability metrics, histograms, so on and so forth. Yes, in the back in the orange.
You mentioned that there was this one line of code which you changed, which effectively reduced the prediction capability of the LSTM model by like 60%, I guess, because it was above 80% initially. The ML was predicting everything, and now it was below 20%, below 0.2. I was just curious as to maybe you could give me just a general sort of idea.
Sure. So what was the line of code, right? It was a very simple change. Go from about 95 down to less than 20. So it was changing a enum that said use static offset versus current offset. And so we just started using current offset, did the exact same experimentation, generated the exact same size data set, and then headed over to Purdue and ran the same model and came out to 0.14. So I will say this, the students definitely were not as happy that they couldn't get back to 95. But from our standpoint, this was great because we designed the algorithm with knobs to begin with. So we didn't say that this is the way it has to work and this is the only way it has to work. We actually built in knobs. And so whether that's the size of the state matrix, how often you update it, the way you index into it. And so even though we had quote unquote compromise, it was a simple fix because we built it into the algorithm. I believe there's a question over here.
I'm sure, I think you already answered this, but it was in reference to how often you update the state matrix. From an adversary, look, have you done any brute forcing methods to see, what is the recommended time to do a state matrix update?
So we have not used any brute force method. And if you don't mind me asking, can you explain what you mean by the brute force method?
Yes, like just trying to you randomly guess, the state that the matrix is in based off of just using, a sequence of numbers like a dictionary, a hybrid dictionary attack, or.
So I would say one of the ideas. So the answer to that is no. But one of the ideas that we originally had was, what if someone was just listening on the bus? Could they build the state matrix by just listening? It's a thing called COVID that kind of shut that down, fortunately. But yes, if I could go back in time or, have more funding for this work, I think having someone just listen and see how much of the state matrix they could build would be definitely beneficial. And at least for the unpredictability metrics we were looking at, I think every 32 frames to every 4,096 is what the work was looking at. And what we found out is, according to the work that we did, the amount of updating should not affect greatly the entropy and randomness in the algorithm. So if you have a choice, why not just wait longer so that you don't necessarily have to spend as much resources updating. But if it doesn't really cost you anything, update it every 5-10 frames, just so that it's just more entropy, more tougher to actually guess. So hopefully that answers your question.
That does. And I'm sorry I missed the first part of your brief. But for the exchanging of the secret key and everything, you're using like a public key infrastructure or
So that was outside the scope of this work.
okay.
We just assumed that if you wanted to participate, you would have this shared key.
All right. I was just thinking like over the net how that approach would be, but
You could use PKI or another variant, but yeah, that was out of scope for this particular work. Joel, you have your hand up in the back for another question online?
Yes, another question came in. Is the timing for node address rotation configurable, or does the protocol force ideal timing?
It's configurable. So in one of the charts we were showing, we were updating every frame, and we went all the way up to updating every 100 frames. And you could potentially do every 1,000, 10,000, 55, 22, really whatever you wanted. And that's one of the benefits of it running on top of the existing protocol. We didn't have to really figure out the timing. If the protocol says, this is how you communicate, within one of our messages is a 16-bit unsigned integer between the value of 0 and 127. And so we don't have to do anything specific for timing. It's just a message like anything else, since it's really overlaid on top of the protocol. Thank you for the question. Any more, Joel? That's it? Okay, so we'll go on to the next project with my remaining time. So this one we just started this fiscal year. We have 2 more years to go on it. So I think ending around September 2024. So I don't have nearly as many slides for this, but it's another idea that we have called CRISP, Computing Reconfiguration for Resilient Space Systems. And it's a way to improve execution in a resilient manner on host. And so here, Jason Hamlet, as I mentioned, my colleague, he actually leads the team that works with Purdue that you see here in the slide. So cyber resilience is really one of the key factors of this particular work. And so a lot of times people say cybersecurity. So the first question is, well, how is it different from cyber resilience? And so what we think of cybersecurity is you make this perimeter, but once you get inside a perimeter, it's kind of fair game. You can do whatever you want. Whereas cyber resilience is really people thinking of, hey, you're going to come inside my perimeter. What else can I do to make it harder that once you do get inside, it makes it harder to do more damage? And potentially, in case of this particular graphic, can I expedite recovery where I can still execute my mission as needed? So not having this assumption that I have this strong perimeter, once you're inside, you have free to lateral movement, but that really, it makes it harder for you to penetrate. If you do penetrate, it's a graceful degradation, excuse me, and then also expedite recovery to hopefully get back to completing the mission. So as I mentioned when I first started, right, space represents this new frontier in cybersecurity. I'm sure you've heard about different things going on in the government that's looking at space. And so what we want to look at is heterogeneous computing platforms. So we've learned that a lot of future space systems are potentially moving away from homogeneous computing platforms and moving over to heterogeneous computing platforms. So we wanted to know that even though this changes because you want to get more performance, can we also use those new systems to improve cyber resiliency? And so to look at what is homogeneous computing platforms, these have been around for a lot longer. Typically, you have a set of compute units that are identical, and you run software that are identical. As you see here on the slide, dual core, quad core, you can have soft CPUs in the FPGA, but everything is identical and everything is running the same software. And so really the big output of homogeneous computing platforms is what we call TMR, or triple modular redundancy. A joke we had earlier today, we're meeting one of the professors, was that when you submit a paper, you may have 3 reviewers, and as long as 2 of those reviewers accept the paper, then your paper may get accepted. So we actually use this in real life. But going back to homogeneous computing, TMR typically has 3 computing units running identical software, and as long as 2 of the units agree, those units typically may save some state and reinitialize the disagreeing unit with that state, and then they all continue forward. Another way you can do it is what's called DMRs. You don't need that 3rd compute unit. The challenge being that if there is a fault or disagreement, you don't know which one is right, which one is wrong. And so you can either go back to a checkpoint, you can reset the system, you can just issue an alarm or a fault, and maybe just wait for someone to intervene. Some of the DMR systems use what's called lockstep, which is at some level, they could actually execute the same instruction in the processor in lockstep. Sometimes there could be a little bit of slack, so maybe 4 or 5 instructions behind, or even something much larger. But typically in lockstep, they're executing at the same time, and the output is checked at some sync point, which could be a checkpoint. Checkpoint is being that every so often I take some image of my state, and I have a way of getting back to that checkpoint. So in case my 2 outputs disagree, I jump back to that checkpoint and then just continue. And so this is how we use typically homogeneous computing platforms. So when you think about heterogeneous computing platforms, and hopefully the colors are coming through online as well, we can see that we have a lot more diversity. We have different compute units. And so these are the kind of platforms that are starting to be used. In particular, we're looking at the Xilinx Versal platform, where you don't necessarily have a quad-core CPU. You don't necessarily maybe have a quad-core, DSP. You don't have enough units to have maybe TMR. And so what we want to look at is, can we look at these heterogeneous computing platforms and still get the resiliency that we had in homogeneous computing platforms, but potentially done in a different way? And looking at space platforms in particular, you may start out with one platform. Here we have the Versal on the left side. And because space systems are built to be modular, you may get additional compute units at some point in the future. So can you incorporate them into your cyber resiliency? And so at the high level, what we want to do is just the same way TCP guarantees network traffic will get across the internet. Can we use CRISP to guarantee execution, or in our case, have resilient execution? And so our first experiment is looking at sorting a 1 million element array in the presence of faults. And we want to know, can we organize the system in such a way that that sorting will always come out correctly, regardless if it's a cyber attack, the presence of ions hitting some of the processors, radiation, any other faults that may happen in the system. But can we guarantee a TMR-like system on heterogeneous computing platforms where we always have the same sorted array? And we're also looking at compression and maybe even a few other algorithms as part of this work as well, just to see, can we guarantee that software will always make progression, and if there is a fault, it can remedy itself on a heterogeneous computing platform. And here on the right side, for the ending of fiscal year 22 and also fiscal year 23, you can see some of the items that Purdue is helping us with at Sandia. They're going to focus a lot more on the algorithm, some simulations, and then we're going to have the physical hardware at our labs and take their output and actually run it, code it up and run it on our physical hardware. So that's the end of my presentation. Definitely want to thank you for your time, having me back again once at Purdue. And now I'll take any questions you may have. Thank you. So is there anything online, Joel? Sure, go ahead, Bharat.
Oh, yeah, hi. Chris, you presented it so beautifully, I can't believe it. Very impressed. And also it's recorded, so many students will be able to listen to this. I don't have any a specific question, but what I want you to encourage is what the students can do.
So thank you for the kind words. So one thing I would say for the students, as always, when you have people come up and speak, definitely take the time to learn a little bit more about their company. Because believe it or not, I was in your seat at one point. And so you are going to school to learn some fascinating facts to be able to give back in your profession and actually work in a profession you enjoy. So definitely afterwards, if you want to talk about internships, I do recruit. So I've been out to about 4 or 5 universities. I'm going out to one in about 2 weeks to recruit. So we can talk about internships and different ways we can get you plugged in at Sandia. So definitely feel free to come up and speak afterwards as well.
When is a good time for students to contact you for the internships?
So we just had our postings go out, I think, this month. And we're probably going to have them close around December. And so the institute that I primarily interview for is called CCD, or the Center for Cyber Defenders. It's one of the premier institutes that we have at Sandia. It's about, I don't know, 30 to 50 students in that particular institute. We have others, so probably for the summer we may have around 1,000 interns or so. But the CCD is really the institute for those that are focusing and want to know more about cybersecurity. And so if you do apply, I could definitely give you the requisition number to apply to, but if you do apply, you may actually talk to me on the phone, do a quick phone screen, and typically I give my assessment back to the people who make the decision. And then if they decide to say yes, then you typically come out in the summer. But the way things have been the last few years, you may even be able to stay and work remotely. I know for myself, we had a few students come out this summer, and I believe 2 of them now are year round. So they went back to school, but they still log in remotely and work on the project that we have for them. So definitely coming out for the summer can turn into year-round employment.
Thank you, Chris.
So
Very kind of you.
Sandia will be on campus September 13th at the CERIAS Cybersecurity Recruitment Fair. And emails will be going out to all of the students who are on the CERIAS affiliated student list, which you can sign up for at www.cerias.purdue.edu/students.
And I believe there's an engineering career fair coming up, and we'll be here as well. So another one of my colleagues who graduated from Purdue, Sylvia, I believe she'll be coming out here as well.
And with that, we are at the end of the class period. Chris, thank you very much for joining us. To those in the room and to those virtually tuning in, thanks very much, and we'll see you again next week.
Thank you.